two different solenoids are coupled through iron core. Many different configurations, but this is sort of the typical. And we make the assumption here that the losses are very small, in terms of leakage of the flux between the two coils. A lot of situations, a lot of geometries too, they may have one coil on top of the other, just for obvious reasons. There's less loss as a result of that. But we determined that depending on the ratio of the number of windings between the primary and secondary, we can transform the input voltage to a desired output voltage. And also we determine the power is conserved in the case where there's no loss of a flux, or there's no leakage of flux. So in reality, there is an efficiency factor associated with this every time that you transform. And this depends on the geometry, how much, and what is the efficiency. And in the case that, the secondary windings are greater than the primary, then your secondary voltage, your output voltage in this case, is higher, and that's referred to as step-up transformer. And in the opposite case, let's say that a very large voltage, coming in the residential area, that you would want to transform that down to 120, and that would be referred to as a step-down transformer. And I have such a thing here on the other side. What's here is a circuit that has two light bulbs. One light bulb is directly connected to the 120 AC, as well as this primary coil here. Primary coil has 500 windings, and this bulb will be connected to the secondary. I mean, I'm assuming you guys can see me on the other side. Is that correct?
Yes.
So what we'll do first is put in the coil that's 250 windings. Remember, the primary is 500. So if I put in a 250, that will be this will now be a step-down transformer. So we'll put this onto this on core here, complete the circuit since we have a complete circuit of the magnetic field, clamp it down, and we'll connect the light bulb to the secondary transformer. And what would you expect would happen here in terms of the ratio of the brightness of the bulbs? Remember, this bulb here, I guess that's the one on your right. So you'll have a mirror type setup on your video. So it will receive 120. What will be the voltage on the other bulb? This is 120. Remember, winding, the primary winding is 500, the secondary is 250.
Would it have half the current, I think, right?
Step down, yeah.
It will have half the voltage. And so in that case, we'll see what happens. I don't know if you guys can see the two bulbs.
We can.
What's that?
We can.
Yeah, we can see it. We can see it.
You can see one bulb is much less brighter than the other. I don't know if it's really better to hit the lights briefly to show this. A little better?
Yes.
That's good.
All right, so now what we'll do next, hit power, remove top bar.
So the brighter one has double the coils?
I'm sorry?
So the one with the brighter light bulb has double the coils?
The brighter bulb is connected directly to the input power that goes into the primary coil, this one here. So 120 goes into the primary, and the light bulb is in parallel with this. it's also connected to the AC. The other light bulb that was less intense, it was connected to the secondary. It's in parallel with that. Okay. So now what I want to do is switch coils. Remember, this is the primary is 500. This is 1,000. This 1,000 turns on this one. All right. So what would you expect to happen in this case?
The second bulb is going to be brighter
Yeah.
because it's going to have twice as much.
Right, the voltage is doubled. Oh, sorry, I went ahead and plugged it in yet. Yeah. 0, there's no voltage. Oh, pretty bright. You guys see that?
Yeah, we
Yes.
see.
Yeah, we could see that. You all right?
Oh, I mean, yeah, who couldn't? So kind of show you what happens. I mean, you know, the current is reduced, but it just depends on how much the load is. It will just tell you what is the maximum load that you can put onto the system. And here's kind of the opposite extreme here. This is a very high step-up transformer. I don't know if you guys can see this, but this is referred to as a Tesla coil.
Lower it down a bit.
I'm sorry? I'll hold it down.
It was too high. It was out of frame.
Okay. And the secondary to primary in this case is about 200. So 120 it goes in, you know, goes into this guy. It's plugged into AC. Multiply that times 200, and that will be the output voltage. And so we should see some excitement from this. Remember, the breakdown potential or breakdown electric field is about, I think it's, remember, it's like 1 × 10⁶ volts per meter. So we're definitely beyond this. You guys see that?
Did you
We
lower
don't
it?
see it.
What's that?
It's out of frame,
Oh,
unfortunately.
you can't see it.
You need to move the camera up.
Alrighty, let's see what I can do. Let me raise up the camera a bit. Now,
Yes.
That's good.
okay, I'm causing a lot of activity with my laptop by doing this. The screen keeps blinking out. And this is a neon bulb. You should be able to see it light up when I connect this to the output. Are you able to see the bulb light up?
Yes.
Yes.
Yeah.
Pretty cool. If I use electric shock therapy, you might need it after this class. Anyhow, I just want to give you some examples here of, for transformers and what they can do.
Okay.
Now, it would be perfectly safe. Well, I mean, it would be a little painful to be shocked by this, mainly because the current is so low. Voltage is very high, but current is very low, you know, much like that in the Van de Graaff. So, I mean, it's not something I would like doing, shocking myself with that, but it's not fatal. Anyhow, also we started on this one problem. I don't know if we really got all the way through it, at least in a systematic way, but I wanted to look here at a situation of how power is delivered to various communities from a power station. Such as here, we have a generator that produces 1.2 × 10⁹ watts of power, which transmits to a town 7 miles away through power lines. These power lines have a total resistance, it's pretty small, 1 × 10⁻⁵ ohms. So what we want to do is determine the power loss in the lines if it's transmitted at 120 volts. And so this is how power is defined. There's really multiple ways, but this is basically like from the power supply or generator is I times the voltage. And so if we want to determine the current in lines, we have the power is given to us, 1.2 × 10⁹ watts. Voltage is 120. So just putting the values for that, we get 10 to the 7th amps, pretty large. All right, so next what we want to do is find the power loss in the lines. Ohmic loss, as some people call it, or IR loss. And that's just I squared times R. So I is given to us now. I mean, we calculated it. And R is given to us. And so we just plug in values for that. 10 to the 7th amps, square that, multiply times the resistance, 10 to the minus 5 ohms. And we get 10 to the 9th watts. This is very close to what we started out with. There's a lot of losses. So if we wanted to determine the percentage of the power is delivered, the power generated, delivered to the towns, it's only 17% as a result of this. However, if we were to, well, anyhow, obviously the large current is the problem. It's better to step up, use a step-up transformer to create high voltage and low current to deliver the power. And shows this case where we have a secondary to primary winding in terms of the transformer that's used is 100. And were to do that, then the current then would be 10 to the 5th amps. The voltage 120 times was 12,000 volts in this case. Of course, in that situation, you have to be very careful about arcing, and so there's a lot of insulation has to be taken into account with that amount of voltage, obviously, as you just saw in the case with the Tesla coil. But moving on from here, we determine the power losses. Now, in the power loss in the lines, just using I squared R, we get now 10 to the 5th amps loss, significantly less than that, 10 to the 9th. If you were to do the, again, the percentage of power delivered, it's almost 100%. And of course, these transformers will only work in alternating current. DC, it will not work, obviously, because you want to change a magnetic field or a change in flux in order for it to transfer energy from one coil to the other. And this is the primary reason why Tesla won the war of the currents against Edison, because of the ability to transform without, I mean, you could, in fact, make a device such that a DC would work, but effectively what you're doing is you're converting DC to AC, transforming it, and then you basically convert it back AC to DC. So it's not very effective. I mean, it's just possible, but it's just extra work. And one thing that could break down. One other thing I thought was kind of cool I looked at, it's the mutual inductance between two coupled solenoids. Here they're coupled by, in this case, is a iron core. So the mutual inductance of the magnetic flux in coil 2 generated by the current coil 1 is given here. Something we already looked at early on. So the two coils, and we're assuming here they both have the same length but different number of turns. So the density is just different. Tightly wound close together over a common iron core. Unity coupling is said to exist between them, as any losses due to leakage of current or leakage of flux will be very, very tiny in this case. Of course, in reality, it's always some factor, efficiency factor you have to take into account. But this is for now for this problem. Consider that only, that assumption. So the magnetic flux inside coil 1, look at that first. We know that stated here is the same in both, actually, but let's first start with, where's my mouse? Okay. So it's the magnetic field in coil 1 times the cross-sectional area. And we know from early on that the magnetic field inside a solenoid is given by this relationship, where we have this extra term, mu sub r is a relative permeability, but mu naught n over L times I. That's something we derived using Ampere's law, if you remember back from the last chapter. Okay, so moving on from that, something we already stated early on, that magnetic flux in coil 1 is equal to that the magnetic flux in coil 2 for this given configuration. All right, so just rewriting what we wrote at the top of the page. This is the mutual inductance. Number of coils in the secondary times the flux in the secondary divided by the current in the primary. Ready? And so now I've written this in the following way. This substituted in. This is the magnetic field. And remember, the flux here is the same as the flux inside the either coil. And the currents cancel. In this case, so they go away. I just rearrange things slightly. I just move an N to 2 inside. This is the number of windings for coil 2. And remember, this can be proved, that the inductance coil 2 from coil 1 equals that from coil 1 into coil 2. Those are equivalent. It's just by symmetry. At least you can show this after about 4 pages of math. So we'll just drop the indices and just call this M. So we just basically have this is the same thing we have written here. Now this is the interesting thing I wanted to show. The inductance in L1 is given by this. It's something we already calculated early on. Okay. And this is the inductance for coil 2. So the interesting thing about this, the geometric mean of L1 and L2 equals M. So if you knew the self-inductance of the first coil and the self-inductance of the second coil, it is just the geometric mean of the two will equal M. Of course, there always is leakage. And if there is leakage, basically you would just have a factor on the outside of this quadratic, and that would, I want to call it K or epsilon, whatever it might be. And that would always be between 0 and 1. 1 is ideal, where there's no flux lost, and 0, all the flux is lost. And usually it just depends on your geometry, what that might be. Typically, it's measured. I just thought this was an interesting relationship.
Professor, what is the value of mu sub r again?
It's the ratio of the permeability of whatever material divided by that in a vacuum. So it's mu divided by mu naught. You know, for example, for iron, mu is roughly 200. For air, it's about 1. For carbon steel, I believe it's about 100. No, actually, yeah, 100. Yeah, it's just, you know, what did I say for regular iron, pure iron? It's like 200,000. It's huge.
So it's a given constant depending on the material that we're using?
It depends on material only, yep. You know, being that we have iron, you know, basically both of these coils are wrapped around a iron bar or let's say cylinder in this case. We have to take that into account. And if this is indeed pure iron, mu sub r would be 200,000, so 2 times 10 to the 5th. Actually, it has no unit since it's a ratio. All right.
Now, the geometric mean of the two self-inductance equaling the mutual inductance, is that general or is that just for
Oh,
the
no,
pure
that's just
mode?
for this specific case. I mean, if
Okay.
these were like, well, you know, even if this was like a loop of, you know, pretty much like we had here in the previous slide, I mean, it would still be close. And ideally, what you would want is have one coil on top of the other. And that it would be nearly the same here. But in the case, like he said, you have these not in the core. I mean, it was not an iron core here between the two. And these were, instead of like lined up with a common axis, but they were maybe vertical instead, not sharing a common axis, I suspect this would not work. So this is really specific to this sort of geometry where the two, coils are linked together through an iron core. All right, so we get on to this, LC circuits. And recall, we have done this in a case, we've looked at RC and RL circuits, current, charge, and potential difference grow and decay exponentially. It depends on the situation where you're charging or whether you're discharging the capacitor. But in the case where LC circuit, the charge, current, potential, they vary periodically, are sinusoidal. A period of, say, T and an angular frequency of omega. The resulting oscillations of the capacitor electric field and inductor's magnetic field is said to be electromagnetic oscillations. A good analogy to this in the mechanical world is a mass on a spring. I think this is something the book alludes to a bit in detail. But let's talk a little bit more about this. At least so we'll break this into like 4 different steps. So here's the circuit. The components are kind of overblown here, but here's the capacitor. Here's the inductor. Okay, and so we'll just look at these some 4 different steps, kind of describing what happens in different phases. So in the circuit, we charge the capacitor with the switch open. Okay, to a potential difference we call VM, like Vmax. The initial charge, reaches whatever, whenever it reaches the maximum. In other words, when the capacitor is completely charged, we call that QM, and that's equal, of course, to C times VM. And then we close the switch. Initially, the capacitor is fully charged. The current is 0. Current energy is stored all in the electric field in this case. And there's no current passing through the inductor yet. This represents the different energies. This is the electric field energy, and this is the magnetic field energy. All right. So the capacitor discharges through the inductor, and as it discharges, the current increases, but the time rate change of the current is slowed as a result of the induced EMF in the inductor. Doesn't like this change magnetic field that's being produced inside the coils. So when the capacitor potential finally becomes 0, the induced EMF is also 0, and the current is leveled off. It's at its maximum of I sub m in this case. So here the electric field now is gone. All the charge, it's been depleted of all the charge. Been moved now, and at this point here, it's been moved like through the inductor. At this point, the inductor is seeing a maximum current and maximum magnetic field. So in this given case, the magnetic field energy, or this amount of energy inside the inductor, is at a maximum. And being that the capacitor is completely discharged, energy, electric field energy is 0. Okay. Although the capacitor was completely discharged in step 2, there's a current still exists. Recall that the inductor doesn't like this to be, for the current just to be shut off instantly. It tries to maintain the flux inside the coils. So then the capacitor begins to charge slowly, much slower in that case as opposed to that in the resistor. And well, it depends, I guess, on the resistor and depends on the inductance. So I guess not necessarily true. Different mechanism. Also, in the case of resistor, some of the energy goes away each time a current passes through. So the capacitor now begins to charge with polarity opposite to that of the initial state. Okay. Eventually, the current and magnetic field reaches zero. The capacitance is now fully charged in a sense, but opposite to that in its initial polarity. You'll notice now on the right-hand side is positively charged, negatively on the left-hand side. And remember, it's the opposite when we started out with in step one. Okay. Now the capacitor is fully charged, the current is zero. The current's energy is now stored 100% into the electric field. Now the process repeats itself, but now it's in the opposite direction. A little later, the capacitor has become discharged, and there's a current in the inductor in the opposite direction, as opposed to that in step three. See, in this case, the current is flowing from left to right, and now it's from right to left. And the current, again, is at its maximum. Now the current energy is stored in the magnetic field. Still later, during this process, the capacitor begins to charge and returns to its original value, and the whole dance starts all over again. It returns to step one. So I wanted to quantify this a bit. So here's sort of a different view of the same circuit diagram that we saw in the previous slide. It's using the loop rule. The voltage across the capacitor is Q over C. Across the inductance is when there's a change of current times the inductance of the inductor. You have an EMF. And since there's no power supply in this system, this is equal to zero. So current is a time rate change in charge, as we know. So we'll make that substitution here into the current side. So we have a double differentiation. And consequently, we have a second order differential equation we need to solve. We want to know the time dependence of the charge on the capacitor. And of course, the derivative of that solution gives us the current through the inductor. Recall we did this early on. The standard solution for a linear homogeneous differential equation is the following. I think a little r is the roots in this case. So we just basically plug this into this differential equation, do the operation. So we take the derivative twice for q, and by doing so, little r comes out twice, so we get a r squared. But the function retains its form. So we still have a e r t. The second part, all we do is just put in the function. There's no operation other than that. But now you can see, since this is equal to zero, this is homogeneous. There's no function of time on the right-hand side. E to the RT, that goes away. We can just cancel that out. And we have this relationship, where little r squared plus 1 over LC equals 0. We move 1 over LC to the right-hand side and take the square root of both, and you see you get an imaginary number. So this is what goes into this test solution here. We call it, this really is a standard solution function for this type of a differential equation. And so this is what we have. Are you guys familiar with the exponentials with an imaginary component? You guys seen Euler's equations yet?
Yes.
Yes?
They go over that really briefly in
The
240.
bottom line is that if you were to expand this out in Taylor series, you would see, you would collect the imaginary part and the real part. And the imaginary part is the sine, it's the same as the Taylor series of the sine function, and the real part is the cosine. Pretty amazing. So this basically will absorb the imaginary part. We can say, well, C1 absorbs. Basically, we can define whatever C1 and C2 is in this case. But this is the solution. This differential equation, you can see it has, this periodic type characteristics. Okay, so let's copy this over to the next slide. So some implications here, but what I want to do is just get rid of C1 and C2 by applying some initial conditions. So let's say at t equals 0, the capacitor is fully charged. And at that same time, t equals 0, the current is 0. But in order to do this, apply this part, we need to take the derivative of the charge with respect to time. That gives us current. And this is what we have here. So by taking the derivative of this first part of the solution, through the chain rule, we have to bring out 1 over square root of LC. And the cosine becomes a sine. And for the other term, the sine becomes a cosine. We still, from the chain rule, we have to bring out 1 over square root of LC. Okay. And we have a minus sign over here in this guy. All right, so let's first, if we were to apply this initial condition for this first part, you say, well, t equals 0, we have maximum of Q max. Well, at t equals 0, the sine part goes away. Sine of 0 is 0. Cosine of 0 is 1. So that would imply that C1 is equal to Q max. Now, in the case for the current, at t equals 0, it equals 0 for that. Well, t equals 0 for this first term, sine of 0 is 0, so that just goes away. And so we just now have cosine of 0 is 1. So we have C2 divided by square root of LC. LC is a finite value. So this means that C2 must be 0 to satisfy these conditions. Consequently, this is what we have. Let's give initial conditions. So this is our time dependence, given these initial conditions for a charge on a capacitor. So now we already determined the current, but let's rewrite this. This is the current here, but also we just keeping the constants here on the amplitude, if we want to call that. There's a minus sign because we went from the cosine to the sine. This means it's in opposite direction. And we want to know the voltage across that inductor. Then we have to take the derivative again of this. I didn't show this. But if you were to take the derivative of this guy here, the current, that will give you di dt. And the derivative of sine gives you cosine. And if you do that, you have this relationship here, but then you bring out a 1 over square root of LC again. So now you just have 1 over LC, right? And since you have a factor of L here already, this is the definition from Faraday's law, the L cancels out. So you're just left with Q max over C. which is the same as that on the capacitor. And that's good. Being that these are basically in parallel with each other, they better have the same, at least, based on that. All right. What we'll do here is just define the maximum voltage is equal to Q max over C. And so now we have this relationship here. Angular frequency, or LC, is 1 over the square root of LC. Is any questions about this? I feel like I'm just moving a little too quickly, but. I'll take the silence as everything's okay. Just kind of refresher, I don't know, summary of things in terms of the frequencies and angular frequencies and how they, how I relate that to the period. Omega is the angular frequency. The period is the time that you have to wait for it to repeat. It's a better good way of describing it. And the frequency is how many times per second it repeats. So omega t, and so you always want to determine, if you want to know what the period is, you would set the argument of whatever, periodic function, sine or cosine, equal that to 2 pi, and then solve for the time, and that would be the period. It's basically just time between the troughs, or time between the crest of a wave or the trough, not where it crosses, by the way. Be a little careful with that. That's actually half of the period. The slope is the same when it crosses here and here. Oh, in that case, yeah, that is another way to determine the period. The frequency is 1 over the period, and of course, the rise you guys already know. Omega is equal to 2 pi times pi times the frequency. All right, it's just a little example here is, say our local radio station on campus broadcasts at 91.3. It's frequency of 91.3 megahertz. If they generate this with an inductor of 1 microhenry, what capacitance should they use? And of course, we're assuming that there's no resistance or no other active elements in the system. But how would we determine the capacitance in such a simple circuit? Is anybody there?
Yeah, you could rewrite the angular frequency equation so that you have the angular frequency over L on one side and C on another.
Exactly. Yeah, that's what I would do. So first, you want to calculate the angular frequency. That's 2 pi times the frequency. This is given to us explicitly. And that's equal to 4.74 times 10 to the 8th hertz. So I did this right. All right, shoot, that's right. Oh yeah, okay. And now we know from this relationship here, what the angular frequency is equal to 1 over the square root of LC. All it is squared both sides to get rid of the square root. Then we can solve for the capacitance and put in the values that are given to us. And it's 3.3 picofarads in this case. And now you can have your own radio show. Playing Led Zeppelin and also talking about physics. I don't know, some of you guys may not have heard of Led Zeppelin. I don't know. All right, so what I'm gonna do now is just look at the energy part of the world in this. Again, this is the time dependence for the charge on the capacitor and the time dependence for the current. This is something we've already determined earlier. So let's find the energy in the capacitor and the inductor. I mean, it will be as a function of time. I mean, we've already derived this early on. The energy stored in the inductor is given by 1/2 times the inductance times the current in the inductor squared. And that's given in the following way here. Of course, the L's cancel. So you're left with this relationship. So this is how the energy in the inductor varies with time. The sine squared times omega t. And recall in the case for the capacitor, is Q squared divided by 2C. And we'll just make that substitution as well here. So now it goes as the square of the cosine times Q max plus 2C. And interesting enough, you can see if you were to add these two together, the energy stored in the inductor and the energy stored in the capacitor becomes a constant. Both of these have the same amplitude. So you just have sine squared plus cosine squared, but you also should remember that's equal to 1. But each individual part does vary. This kind of sloshes back and forth between the inductor and the capacitor. And here's this little drawing here that shows basically what's going on. The blue part is the capacitance. At T equals 0 is at a maximum. Of course, there's no current initially in the inductor, which is red here. And basically, you can see it just goes back and forth. Yeah, as I said earlier, if you were to add these two together, you see energy is conserved. But that only happens here because we're considering an ideal case here where we're not considering resistance in this circuit. And if it was resistance in this circuit, for every cycle, the amplitude would go down. It would not come back to its original energy in this case, which should not be surprising. Where does it go? Well, it goes into the resistor. The resistor is heating up. You can think of the molecules inside the resistor. It's just wiggling more than it was before each time the current passes through. Of course, there's no current that's passing through at the time where the capacitor is at its maximum charge. But yeah, let's just move on to that. This is a good segue to here where we're considering an RLC circuit. And now we have a little longer differential equation, but actually the solution is no different in terms of plugging in a value. Remember it's a to the ERT, little rt. So this is our second order differential equation, but now we have this midterm is the wrong word, but this single differential. The second order part is the first order and 0 part. Again, we just use our standard solution. Again, this just only works for a linear homogeneous differential equation. So we'll plug this in, and this is what we get. So when we plug it into the second order part, we differentiate this 2 times. And so R comes out twice. The beauty of the exponential, regardless how many times you differentiate this linear differential, linear exponential, it retains its form. Second term, we only differentiate once, so R only comes down once, little r. So now you have the resistance times little r times this function, It's the standard solution function. And all we do here is there's no operation that takes place for the first term. So again, the e to the RT just goes away. And we're just left with this relationship that we need to solve. We need to solve for little r. And this is a quadratic equation. So solving r requires a solution to the quadratic polynomial, if you want to call it polynomial. It's a quadratic equation. I'm sure most of you guys are familiar with this. Alrighty. So now is what I'm going to do here, just to simplify this, is just pick the positive solution. The negative solution, as it turns out, you just have a phase of 180 as a result of that, but that's not really necessary to go into. So we're just going to pick the positive solution, substitute that into the exponential, and this is what we have. And note, if r is 0, we get back to what we had just for the LC circuit. So it's consistent with that. So let's look at this a little bit more. Just copying this over to the next slide. So depending on these values, the circuit R, LC, imaginary component is possible. Not necessarily. It depends on the values, of course. Consequently, there are two cases we must consider separately, as they have very different properties. Now, in the case where R squared is greater than 4 times the ratio of the inductance divided by the capacitance, and in this case, there are no imaginary components to the solution, right? Consequently, the charge will not oscillate between the inductor and the capacitor. It'll just basically just have like an exponential function in this case. This is referred to as being overdamped. More interesting part is where R squared, the resistance squared, is less than 4 times the inductance divided by the capacitance. And in this case, you have both an imaginary part as well as a real part. What I've done here is I've pulled out the real part, the minus R divided by 2L. That's real. That just comes out as an exponential. This is the imaginary part. And that contributes to the oscillations. Let's added a phase here. Phase, because I'm not showing both sine and cosine. So for every oscillation, the amplitude decreases over time.